All right, well, thanks, Tim. In my talk today, I'm gonna give just a really brief overview of the Potlatch River IMW, and then I'm gonna discuss some of the recent life cycle modeling we've been doing, and then I'll be finishing up with just a future sort of outlook of our project. All right, so the Potlatch River is one of two IMWs in Idaho. It's located in the northern part of the state here at the base of the Panhandle. The Potlatch is the largest tributary to the lower Clearwater River, and it supports a wild steelhead population that is critical to recovery efforts of steelhead throughout the Clearwater Basin. In addition, there's an active restoration program going on in the Potlatch focused on improving freshwater spawning and rearing habitats in order to boost steelhead numbers. So within the Potlatch, we concentrate the bulk of our monitoring and restoration efforts in two watersheds, Bear Creek in the lower Potlatch and the East Fork River in the upper Potlatch. Now, these watersheds were chosen in part because they support some of the highest densities of juvenile steelhead in the basin, but they also represent the diversity of landscapes that we see in the Potlatch. So the Big Bear Creek watershed is characterized by these steep canyons rimmed by rolling cropland. Now, much of the uplands that was once timbered or meadow has been converted into agriculture land, but these canyons have remained relatively intact over time. Now, our primary limiting factors in Big Bear Creek are low summer base flows and tributary blockages, both of which severely restrict the amount of juvenile rearing habitat. And so our restoration strategies in Big Bear Creek are focused on expanding juvenile rearing habitat by removing barriers and supplementing summer stream flows. Now, in contrast, the East Fork Potlatch River is characterized by timbered hills and high meadow terrain. Now, the East Fork remains perennial throughout the year, so flow conditions aren't a problem in the East Fork. Rather, the primary limiting factors in the East Fork are a lack of pools and in-stream cover that is critical to juvenile steelhead. Due to past logging practices, many of the reaches were either straightened and the riparian vegetation and in-stream wood was removed. And so our primary restoration strategies in the East Fork are really focused on increasing the in-stream habitat complexity and improving the riparian function. And we do that through installation of wood in key areas, re-meandering stream channels, planting riparian zones, and excluding cattle with fencing. Now, moving on to our monitoring, we use a hierarchical study design with 3 levels of monitoring to evaluate fish and habitat responses in the Potlatch. Now, the broadest level is our index watershed monitoring, which is intended to measure the total benefits of all restoration on our 2 study populations. Now, this monitoring is set up in a before-after comparison of steelhead production and productivity in the watershed. And we utilize a combination of rotary screw traps, pit tag arrays, as well as adult weirs to monitor adult escapement, juvenile emigration, and ultimately smolt per female productivity. Now, our next tier of monitoring is our tributary level monitoring, which helps us isolate responses to restoration types. Now, this monitoring is set up in a Backy design where we're looking at both treatment and control areas. And in the lower Potlatch, the treatment streams are the Big Bear Creek, Little Bear Creek, and the West Fork of Little Bear Creek, and our control is Pine Creek. And then in the upper Potlatch, our treatment area is the East Fork Potlatch, and our control is the West Fork. And here we use single-pass electrofishing and snorkel surveys to assess juvenile density. We do roving pit tagging to monitor juvenile survival and growth, and we can conduct habitat surveys to monitor key habitat variables over time. Now, lastly, we also monitor several high-priority projects at the reach scale to determine the localized response of steelhead to a particular treatment. And this monitoring is really customized to individual projects. And in general, we utilize techniques such as electrofishing and radio telemetry to determine the steelhead response to a particular treatment. Now, in addition to the monitoring that I just described, we've recently developed a life cycle model that allows us to assess potential changes in steelhead production to future restoration actions. So at this stage in our project, we're currently in the treatment phase in both of our index watersheds. And to date, we've documented positive responses in both fish and habitat at the reach scale. We've also seen some positive trends in key metrics at the tributary level. But the scale of restoration hasn't been great enough to generate a population level response in either of our watersheds. And so we constructed this model in part as a tool to help us strategize and prioritize future restoration actions. With the uncertainty of funding, we want to be able to implement those high impact projects more efficiently in order to generate a response in the shortest time frame possible. So this is just a flow chart representing the mechanics behind the model. I'm not going to get into the specifics, but what I do want to say is we fit separate models for each of our watersheds, and we utilize data that we collected in our watershed monitoring, such as dot escapement and emigration and life history data, to parameterize the model for each of the watersheds. We conducted separate modeling scenarios for each of our watersheds. I'm going to start with Big Bear Creek, and then I'll touch on the East Fork. So what we asked in this first scenario is, what is the potential smolt response following the implementation of 3 large-scale barrier removal and flow supplementation projects in the watershed? Now, these 3 projects are in various stages of implementation, but they're all focused on expanding juvenile rearing habitat. So this is a map here showing the location of the 3 projects, and this green highlighted area is a conservative estimate of the treatment reach for each of these projects. And combined, these projects could open up and restore access to nearly 35 kilometers of additional habitat. Now, we know not all of this habitat that's being opened up is of good quality, so we used some data that we had from our habitat surveys to sort of refine this estimate and quantify the amount of quality habitat, which is this yellow bar here. And so in this modeling scenario, we modeled the potential smolt response, assuming that these 3 large-scale projects would restore nearly 29 kilometers of additional rearing habitat. All right, so we'll move on to some of the results here. So this is population productivity data for Big Bear Creek in terms of the number of smolts on the y-axis and spawners on the x. And to date, we have generated 9 complete brood year productivity estimates for Big Bear Creek, which are represented by these black dots here. Now, the yellow dots are simulated outputs of the model under our current conditions in Big Bear Creek. And if we just focus on the distribution of the yellow and the black dots, you can see that the majority of these simulated values do fall within the range of the empirical observations, indicating that the model is doing a good job, performing well, and doing a good job characterizing our current conditions. Now, this dashed line here indicates our current productivity curve in Big Bear Creek, and then the gray dots are the potential productivity curve there after the implementation of these projects. Now, I really want to focus more, though, on the changes in smolt production, because that's really what these projects are geared towards focusing on. So this is our current smolt production modeled out here in Big Bear Creek. So on average, we see around 10,300 smolts annually coming out of Big Bear Creek. Now, in comparison, this is the estimated smolt production following the implementation of these 3 large-scale projects. The model estimates that smolt production would increase upwards of 85% to nearly 19,000 smolts annually. Now, this is a very substantial increase, but it isn't too surprising considering that these projects effectively would double the amount of rearing habitat that we currently have in our watershed. So we expect to see a sizable change in production as a result. So moving on to the East Fork here, the question that we asked in this modeling scenario is, what is the potential smolt response following the treatment of 15 kilometers of habitat with large wood or riparian treatment. And this 15 kilometers represents the amount of planned treatments over the next 5 to 7 years in the East Fork. And it would represent about 25% of the core distribution area of juvenile steelhead in the East Fork. Now, unlike in Big Bear Creek, where we're modeling just an expansion of marine habitat, these large wood treatments could affect either the carrying capacity or the intrinsic productivity of the system. And so we modeled changes in smolt production, assuming that these large wood treatments would increase juvenile densities to some target level. So this map here shows our average juvenile steelhead densities from our electrofishing surveys in the East Fork, with the higher bars representing higher density. And I should point out before I get going on this that we have documented a strong positive correlation between juvenile densities and large wood in the East Fork. But this relationship varies spatially, as you can see here. So we see our highest densities of juvenile steelhead in the upper part of the drainage with estimates of around 7 to 20 fish per 100 meters squared. And this is also where we see our highest densities of wood in the system. And as you move downstream, both the densities of fish and the densities of wood decrease. And this lowest reach here has the lowest densities of both fish and wood. And this is where the bulk of those planned LWD treatments are going to take place. And our goal is to increase densities in this lower part of the system here to more comparable to what we see up here. So in this modeling scenario, we modeled the change in smolt production, assuming that these large woody debris treatments would increase juvenile densities from our current estimate of around 6.5 fish per 100 meters squared to 20 fish per 100 meters squared. Now, once again, this is a similar population productivity graph that I showed earlier for Big Bear Creek with smolts on the y-axis and spawners on the x. Now, in the East Fork, I think we've generated 6 complete brood year productivity estimates. So these are the black dots here. So these are values that we collected through our monitoring. And once again, the yellow dots are the simulated values under our current conditions. And you can see that the fit of, most of these yellow points are falling within the range of the black dots or empirical observations. The fit isn't as good as in Big Bear Creek, but it's okay. It's likely because we have fewer data points to begin with. And once again, the gray dots indicate the potential productivity after the implementation of these projects. Now here is the estimated smolt output under our current conditions in the East Fork. And the model estimates we see around 19,000 smolts annually coming out of the East Fork. In comparison, this is the estimated smolt production following the implementation of these 3 projects. The model estimates that smolt production would increase to around 27,000 smolts annually, which would represent about a 40% increase in production. Now, this increase isn't as drastic as we saw in Big Bear Creek, but it does suggest that this level of treatment would generate a detectable response. So now I'd just like to talk about one example of how we can leverage this data from the model to help us in prioritizing future restoration projects. And in this example, I combined outputs from the model with project costs to determine the cost effectiveness and compare it across these projects. So this first graph here is just the estimated smolt increase for each of the projects. And for comparison's sake, I broke out the individual projects in Big Bear Creek and I scaled the East Fork results to a single project. And in terms of potential impact, Big Bear Falls project would have the greatest potential impact. Now this figure here is the cost estimate for each of these projects. Once again, the Big Bear Creek Falls project would be the most expensive and the Culver project would be the least expensive. And then if we combine these 2 data sets, you can calculate a cost per smolt estimate for each of these individual projects. So in this example, in comparison, the Big Meadows Creek culvert has the lowest cost per smolt, or in other words, would give us the biggest bang for our buck amongst these projects. Now this is just one example of how we can utilize this data. It could come in handy when there are multiple restoration projects competing for limited funds. And it just gives us another tool that we can use to evaluate future projects. So lastly, I just want to finish up with just a brief outlook of the future of our project here. In terms of monitoring, I feel as though we've really developed a solid framework, a monitoring framework, and we're well poised to evaluate any steelhead response in the future. Now, we've made some critical additions to our monitoring over the years, and we'll continue to adapt and refine aspects of our monitoring as needed in order to increase our power of detection. Now, in terms of restoration, over the course of this project, our restoration program has matured, and we're starting to see significant improvements in the pace of project implementation in our watershed. And to kind of illustrate this point, I just want to highlight some of the progress that's being made in Big Bear Creek. So in the first 5 years of our project, progress was pretty slow in Big Bear Creek in terms of restoration, and we really only implemented one relatively large-scale barrier removal project, which is the Dutch Flat Dam site. Now, during this time, our restoration partners were getting the programs established, and they were spending considerable time and effort generating interest and establishing relationships with landowners in Big Bear Creek to get projects on the ground. Now, within these past 5 years, we've seen a substantial increase in the number of projects that have been implemented in Big Bear Creek. And we're seeing progress made also on some of these high-impact projects that I was talking about earlier, such as the Big Meadow Creek Culvert project, which was completed this year. And moving forward, we hope to keep this momentum up. And there's a priority to finalize and get these large-scale projects implemented. And we anticipate that we'll get all 3 of those projects that I talked about in the modeling implemented by 2023. Now, we're seeing similar progress in the East Fork, and I believe we anticipate around 20 kilometers of the East Fork will be treated by the 2023 date here. And so really overall, in terms of the project, I think we're at a really critical stage, and we've got some really high impact projects coming online, and I'm really excited to see what changes we're going to see in the steelhead population as a result. And with that, I'd just like to acknowledge the funding sources for our project, as well as our folks doing the restoration work in the watershed. Thank you.